Let's work through the analysis of the insertion sort. We'll use the same 6 values that we used in the card animation process, and remember we start with value in position 1, trying to find the best place for this. Now before we do that, we need to save a copy of it, so I'm going to indicate that right here, because we immediately see that this is a better place, so we shift the 5 over, and that clobbers the 3. So it's no longer in the list, but we've saved a copy, so we're good. Then we detect we're at the beginning of the list, which is a comparison step, and that's where we put the 3. So the list now contains 3, 5, 7, 1, 2, and 4. And that's the end of the first pass. To count this, we're going to consider 4 things. We always have the initial save step and the final insertion step. And then we have several comparisons in between. We'll always have one less shift than the number of comparisons because the final comparison is the one that finds the best place. So here we had one shift, but we compared it to the 5 and to the step out of bounds. So our total is 5 steps for this one. Now we'll try to find the best position for the 7. And so we save a copy of the 7 up here, and we see that that's not a better place. So the 7 just goes back into place. And so again, we have 3, 5, 7, 1, 2, and 4 after the second pass. And this is always going to be the most efficient type of pass. We still save, we have one comparison that says, nope, we're in the right place, and we put it back. So the total cost is 3. Now let's find the best place for the 1. Well, we save a copy of the 1. The 7 shifts over, so that's now a 7. That's a better place, so the 5 shifts over. That's a better place, so the 3 shifts over. And now that's stepping out of bounds, so the 1 is going to go right there. So 1, 3, 5, 7, 2, 4, and that's the order after the third pass. The cost here again was the initial save and the final insertion, plus 4 comparisons and 3 shifts for a total of 9. Now we'll find the best place for the 2. We save a copy of the 2. The 7 shifts over, the 5 shifts over, the 3 shifts over, but that's not a better place for the 2, so that's where it's going to go. So we have 1, 2, 3, 5, 7, and 4. And that's the end of that pass. Total cost, well, again, we have the initial save and final insert. We had 4 comparisons, 3 shifts, for a total again of 9. Now let's find the best place for the 4. We save a copy of the 4. 7 shifts over, 5 shifts over, 3 does not. So that's the best place for the 4. So we end up with 1, 2, 3, 4, 5, and 7. And that's the final sorted list. So we had the initial save and the final insert costing 1 step each. 3 comparisons, 2 shifts for a total cost of 7. So if we add all these up, we've got 5 plus 3 is 8, plus 9 is 17, plus 9 is 26, plus 7 is 33. So our total cost is 33. Now, the analysis of the insertion sort is very similar to what we saw in the selection in the bubble. It's an n-squared sort. It's a quadratic sort, and that's another name we use for these 3 sorts. The average cases like this one, our total cost was 33, which is very close to 36, making it a runtime of O of n squared. The best case would be when the elements are already in order, and the cost of this would be 15. And if you think about it, when we did the 7 over here, it cost us 3 steps. So for every one of these elements that's not the beginning one, that would be 3 steps. So 1, 2, 3, 4, 5 times 3 would be 15. So that's very close to O of n, closer to O of n than n squared. Even if it's twice n, it's still closer to n, and it's considered an n running time. The worst case would be when the elements are in reverse order, and in this case it would cost us 52 steps, still closest to 36, which would be n squared. So in conclusion, the insertion sort is relatively stable, best used to verify a sorted list, which would cost O of n, and worst when the list is in random or reversed order with a running time of O of n squared. Now it's time to take a look at the insertion sort pseudocode and see how it works. Generally speaking, it's a loop inside of a loop, used to find the best place for the value. And here it is. And if you study it carefully, you'll see there is no swap process used here. It's inherent in the process itself. So let's take a look. The king loop starts at 1 and goes all the way to the end of the list. This is the saving step. We're saving the value that's in the current king position as well as that position. Now, even though it's 2 steps, we're still going to count it as 1 saving step. This is the loop that goes down towards the front of the list and makes sure that we're not out of bounds and that the position that we're looking at is a better place. If that is indeed the case each time, we shift it over and then we resave the position of that. So that's the end of that while loop. And here we finally insert the temporary value into the best place. So study this code carefully so that you totally understand what's going on with the insertion sort.